Questions? All right. So where we last left off, we talked about, of course, keep up with the reading. We talked about linking and loading, and we talked about two approaches of linking and loading. One was called static, and one was called dynamic. And in the static case, you have a library of routines, and that library of routines has the implementation of the functions that your program is going to be using for its system calls. And when you do this static linking, and we saw this in the make file when we did a GCC-O, the name of the executable space, and then the name of the object file that you just compiled. And we said that when you create the executable, when you're doing this static linking, you're literally pasting together that object file, that file from the operating system that has a library of system call implementations. You're pasting it together with the object file that you created to make a single executable. Conversely, with dynamic linking, you're pasting together something from the operating system with your object file. Yes, that doesn't change. But in this case, it's not the entire library of routines provided by the operating system. It's a small piece of code that knows where to go to load this library of files, and that's called dynamic linking. And so when you run your program in this case, that piece of code will then search for, in a number of well-known places on your operating system, search for those library of routines that implement the system calls made available to your program by the operating system, and it'll load them when you run your program. And so the idea there is that why should you load all this stuff into memory unless you're actually going to use it? And these dynamic dynamic linking and dynamic loading, these object files from the operating system, they're called SO files, or for shared object on Linux and UNIX, and they're called DLL for dynamic link libraries on Windows. So when you browse around on your file system on Linux distribution, you see .so files or DLLs on Windows. That's what they're for. Okay. Any questions about this from last time? So we left off? Okay. So let's take a look at the operating system interface. And each operating system, when you think about what an operating system is very closely tied to the hardware that you have. So for example, an operating system associated with hardware that has a touchscreen or voice interface is going to devote a lot of code and a lot of system calls for interacting with those particular devices associated with the machine. And so there are certainly a set of services that are provided by your operating system, and those services are different depending on what hardware is available and also depending on the application that you have. In fact, oh, let me take a pause. Did I address your question with the point in the morning? Okay, great. All right, I just remembered I said I would get back to you. All right, so there are different services provided by your operating system. Those services are specific to the hardware. And you have different operating systems. You can have certainly common set of APIs, and that's what people have tried to do, especially for things like POSIX, right? You have different Unixes, and people decided, got together, formed a consortium, and said, you know what? Let's decide on a set of system calls to provide a consistent interface, and we're going to have all the Unixes support it. Now, just because you use POSIX, it doesn't mean that's the only set of interfaces available on Linux or Unix. There are certainly other distribution-specific APIs or services that are available. And so these APIs typically concern things like user interfaces. So if you take this new camera on that was introduced on the iOS, the depth camera, right? You're going to have kits available, as Apple likes to call them, which are a set of APIs that allow you to write software that make use of this depth camera. And so one of the applications is for logging in, right? It uses the contours of your face, which is unique to each person, to authenticate you to the machine. Touchscreen gestures, I/O, and libraries for things like 3D cameras, augmented reality, and so forth. And there are other types of interfaces, something called application binary interfaces. These are the binary formats that these platforms, the operating system specifically, that they expect of any executable that you want to run. On Unixes, there's something called the ELF binary format, and there are all sorts of binary formats available. And if you want to run on the machine, of course, your executable has to be formatted adhering to the specification for these various binary interfaces. You can also circumvent this need for a specific binary interface through interpretation. And so languages like Python and Java, and those aren't the only ones. Lisp is interpreted. They're interpreted languages. So that means when you run them, the text of your program, its behavior is made possible, or the semantics are implemented by a runtime that happens to be a piece of software. So when you run a Python program, you might type Python space at the command line and then the name of the .py file. The .py file is your program file, but the Python executable is your runtime interpreter. Now, of course, you can certainly have a .py file, and if you put the right information at the top of that .py file, you can just run the .py file directly from the command line, and it'll go find the Python interpreter and run it. So these interfaces are intended, these interpreters kind of shift the burden from your operating system to this process that implements your runtime, namely the interpreter. And in that regard, you can physically, regardless of the operating system details that's hosting your application, you can literally take the same source code and run it on multiple operating systems. Now, Java is called a Java interpreter, right? The virtual machine takes the bytecode, which is the binary code for a fictitious processor called the Java bytecode interpreter. And this processor knows how to interpret the binary format for Java programs. Now, Java is an interesting one because the Java interpreter or virtual machine, it can be implemented as a process at user level. It can be implemented in the kernel, so very tightly linked with your kernel and very fast. It can also be implemented in hardware, right? There are native Java interpreters where the hardware itself in the chipset, a coprocessor alongside the main CPU, just think of it as a second CPU, knows how to interpret the Java bytecode. So this interpretation allows you effectively to write once, as it were, and run anywhere. Well, not anywhere. There's a little asterisk on that. Anywhere for which you have an interpreter implementation. Okay. So let's take a look at a little bit of high-level details about the design and implementation. And so there's no one way to design or implement an operating system. It's not a solvable problem. There's nothing that says you must implement an operating system this way. You could choose to structure it in a layered approach. You can choose to have one big ball of code, and there are reasons why some people feel it's important to do that. You could maybe structure it as a finite state machine, right? You could structure, from a software standpoint, your operating system however you want. There's no one way to do it. It's not really a solved problem. And therefore, the internal structure of different operating systems is different. And there are historical reasons. Maybe one operating system started as an extension of another, or maybe somebody had a particular feature need, like real-time performance, so they took Linux to create the RT Linux distribution, and they needed to change it in order to accommodate something called rate monotonic analysis, right? So the structure internally of operating systems can be different. And what you do when you create an operating system, you start by looking at the goals that you have in mind. Maybe your goals are that this operating system will run on a platform that has very limited memory. Or maybe this operating system, it cannot crash, but you want to allow people to change the way it does things like memory management and file management. So you first, like any good piece of software, like the design of any good piece of software, you want to look at the goals that you have in mind and also the specifications. What do people need this thing to do? Now, the biggest, most complex types of operating systems are so-called general purpose operating systems. Those are things like Microsoft Windows, Mac OS, and they're called general purpose because, as the name implies, you can use it to do a whole host of things. Now, if you take, for example, you buy a modern appliance like a refrigerator, washer, dryer, dishwasher, and so forth, the operating systems those run, they're not general purpose, right? They're only there for very specific single purpose. Take automobiles, right? The operating systems that run the car computer for most modern automobiles, those are have very particular purposes, right? They are real time, so things have to happen in a certain amount of time, and they're very, very small. And the systems on which they run have to survive a lot of adverse conditions: heat, temperature, moisture, and so forth. So you start out with the goals and specifications that you have, and certainly the biggest driving or impacting factor in the goals and specs of your operating system design is the underlying hardware, right? Because certainly if you're going to interact with some peripheral, and a peripheral, in a general purpose operating system might be something like a printer or the network and so forth. But in something like an automobile, it might be your transmission, it might be your anti-lock braking system. And so certainly the hardware that you have in place, both the processor as well as the peripherals, are going to impact greatly the design of your system and the structures that you have in place. Now, some of you might get a chance to look at the internals of an operating system, but if you never look at the internals, it's still important to understand these considerations because that's going to help you design better applications. Okay. Any questions about this? No? All right. So there are user goals in place and there are system goals. Now, when you look at the users, you have to think about who that user is. Right? For an automobile, well, the users don't really typically see the operating system, and they shouldn't, right? You don't want to have a command line interface in your operating system. You want someone to be able to pull up, maybe it's the radio console, and to be able to select something by pressing buttons. You don't want someone to have to type at a keyboard in order to access some feature of your car. That would be horrible. And so the user goal, right, is typically one where it should be easy to use. And so that means, like any good design, you want to identify who your target user audience is. If your user is the mechanic in the repair shop, right, then you want to know what he or she might find important as it pertains to interacting with this system. So for the most part, it should be easy to learn, easy to use, reliable, safe, and fast. It should be responsive as it pertains to the user experience. Now, the system goals, you want to think about things like maintenance, design, upgrade, and things like that. It should be easy to design, right? It shouldn't be a big pain when you're trying to develop it. Easy to implement, also easy to maintain, and that maintenance part is really, really important. Now, I don't know about you, but for a car, I can't tell any time ever where I had to upgrade and install a software patch for my car computer, right, on my automobile. Maybe you have, but probably not. So a lot goes into making them reliable, right? You can't have bug fixes that you have to upload every month on a car. It just wouldn't work, right? So this part about maintenance and error-free and efficiency, that's a system goal, right? When you're trying to implement this. Now, of course, something that satisfies a system goal might not always satisfy a user goal. If you want something to be small and efficient, well, you can't have fancy user interface because that's not small and that's not efficient. It takes a lot of code and a lot of processing in order to do things like redraw pictures. It takes a lot of processing when you minimize a window. Instead of the window just minimizing, you see it animate, shrinking down into an icon, right? That takes processing power. And so just because you have a user goal, it doesn't mean that is amenable to system goals and vice versa, right? Sometimes you have to make compromises. Okay, and so a really important point you're going to see throughout the remainder of the semester when we talk about things like process management and memory management and file management is this idea of policy versus mechanism. Now, this is really, really important from a design perspective. It's this dichotomy that talks about what you do, i.e. what decisions are made in the operating system code when it runs, and what facility that you have in place in order to implement that or make it possible. So policy talks about the what will be done, and mechanism talks about how you do it. So one example is when you're implementing a file, there's this notion of a file block. And a file block is nothing more, or inode on Unix, is nothing more than a contiguous block of bytes that are going to be stored on disk. It's a so-called on-disk data structure. And within that file block, you might have permission bits. Now, the permission bits would be the mechanism by which you implement file access permissions, but the policy would be, okay, whoever is the user is the creator of this file is the only one who can write it, right? And so this idea about separation of concerns, as it's called in software engineering, the separation of concerns between policy and mechanism is a really important one in an operating system, right? Because you can change the mechanism, but the underlying policy shouldn't be disturbed if you're going to upgrade the implementation of how something is done. Maybe you want to introduce an efficiency, okay? All right, so mechanism determines how to do something. Policies describe what is to be done. And the separation between the two is very important because it allows your system to be flexible, right? You can upgrade your implementation for things. Okay? Any questions about this? Yeah. So it's been said, if you really want to master software engineering and data structures, write an operating system, look at the source code for an operating system, tinker with it. Same goes for compilers. It's a very highly creative software engineering process, and you will see just about every data structure you studied in data structures and algorithms, and you'll gain a really, really deep appreciation of why algorithms are important and runtime analysis when you go into the internals of an operating system. Now, the good news is there are a lot of free operating systems that make the source code available to you. So there's nothing precluding you to just tinker in your spare time, especially if you're on the job market in the next year. You can say to your potential employer in an interview, well, I've been looking at this subsystem in the Linux kernel and been doing the following work, right? It's a wonderful way to gain an advantage as it pertains to the job recruitment process. Okay, so there's a lot of variation, and many operating systems these days have their parts implemented in a number of different languages. And why different languages? Because some languages are better at some things than other languages. Now, some operating systems in the early days that were written in assembly, right? And thankfully, that's not the case. My first internship in college was to write in assembly code. It's very doable, but it's very tedious. And so when systems languages started coming out, like ALGOL and PL1, which was a precursor to Pascal, and many of you are too young to remember Pascal, but now C and C++ are the predominant so-called systems languages. And they're called systems languages because they expose all the details of the system, like memory and file handles and things like that. They expose all of those details to you. Take, for example, a language like Java. Java has so-called garbage collection. And what garbage collection is, it's an automatic way by the Java virtual machine and runtime for tracking all of the memory that you allocate. When you say new some object name in Java, you're allocating memory when you instantiate that class into an object in memory. Now, Java keeps around a hash table, and every time you make a reference, this thing called a reference counter on the hash table entry for that object instance is incremented. And once your block goes out of scope or your block ends, if there are no more references, it decrements every time a block ends that has a reference. And once the reference count goes to zero, the garbage collector goes through the hash table and it looks at all those objects that have a zero reference and it goes ahead and deallocates it for you. Whereas if you contrast that with C and C++, if you allocate an object or some data from memory, so malloc in C or new or malloc in C++ as well, you have to take on the responsibility of freeing that memory when you're done with it. It's not done for you automatically. And if you don't, as your program runs over time, it'll keep allocating memory, allocating memory, allocating memory, never releasing it, resulting in what's called a memory leak. All right, so you've ever seen some programs where you run them for a while and you leave them running, your system gets really, really sluggish, and then eventually it freezes up or the operating system kills it off. That's because your program has a memory leak. Okay. So you have lots of different programming languages that are used to implement your various aspects of your operating system. And some make use of so-called scripting languages or shell scripts. When we showed the command line interface, there are ways of chaining together these commands in a type of program using a so-called scripting language. And the scripting languages, there's Perl, there's shell script. Python is considered a scripting language, even though it is a programming language. It behaves just like a scripting language. So it's typically categorized as a scripting language. And so when you implement parts of or a whole operating system in a high-level programming language, it allows you more easily to so-called port that operating system to different hardware. And so porting is just the name ascribed to when you take the code and you recompile it on a different platform, and there are other pieces that might break, they might not work because maybe the underlying hardware doesn't have those facilities. So you have to then implement things in order to get it to work or re-implement parts of it to work on that other hardware, right? And that process is called porting. So you're taking the details of one hardware platform and changing the source code if needed in places where it needs to change in order to get that operating system to run on a different piece of hardware. Okay. So if you, for example, there was a new chip embedded system or something like that that came out, and you wanted your particular favorite version of Linux to run on it, but Linux has never run on it, you would have to go into the internals and change parts of the Linux kernel so that that kernel will run on that particular piece of hardware. Okay. There's also emulation, and emulation allows an operating system to run a piece of code that's not native to the underlying processor. So when Apple switched from the Motorola processor to the Intel processor many years ago, they had an emulation layer so that people could still run their old software on the new platform. Because when you're dealing, especially in industry, people spend a lot of time and money and training on particular software, and you can't expect an organization to switch to new software just because the underlying hardware platform has changed, right? That doesn't happen because you can imagine an organization with, say, 5,000 people, and you have a software stack that everyone's using every day for productivity. You can't expect them all of a sudden to learn something new. That's a huge training cost, upgrade cost, and so forth. So it's often the case when something changes in the underlying hardware on which the operating system runs, that you'll have an emulation layer that takes the binary interface, the application binary interface for the old system, and it allows you to run those same programs, but there is a slowdown. You get that support of the old software, but the cost of that emulation to support the old software is a slowdown in performance. And the idea there is that over time, that you're going to eventually upgrade your applications. Okay. Any questions about this? Make sense? Okay. So operating system structures, there's all sorts of structures in place that have various assumptions based on the design goals of various popular operating systems. And so MS-DOS, MS stands for Microsoft. Microsoft, the whole story, the history is interesting. If you ever want to look at it, just Google search it. But Microsoft wrote MS-DOS under a contract, and MS-DOS was, the first, I won't say the first, but a very general purpose, widely used operating system for individuals on personal computers. And so MS-DOS is very, very simple. And the whole purpose for MS-DOS was to provide just the smallest amount of layer on top of the basic hardware and device drivers to allow applications to run. And when MS-DOS loaded an application, it gets out of the way. And the application that's running, only a single application, has full use of the machine's resources and the operating system's resources. So it's a so-called single tasking operating system. UNIX is more complex, and those complexities introduce ideas about multitasking. So if you're going to add new abilities and capabilities, certainly the structures underlying it are going to also increase in complexity. There are abstractions for writing operating systems, such as layering. As the name implies, you have different layers or different sets of functions, and those functions collectively handle a certain type of feature, and they present an interface, and a layer is more of a logical construct that says, I perform some type of behavior, and when I need to use some other behavior, I'm going to make a function call from a different layer or collection of software routines. Okay. There's also an arrangement or structure for operating systems called a microkernel. And an early example of that is the Mach operating system. And Mac OS is based on parts of Mach operating system as well as Berkeley Systems Division or BSD Unix. Now, Mach introduced the idea of a so-called microkernel. Well, Mach didn't introduce it, but in terms of popular operating systems, they were one of the first to use microkernel. And with a microkernel, I'll show you in a few slides, the idea is to take things like your file system and to implement them as services and not have them inside the kernel itself. And the reason for that I'll talk about a little bit later. So this is what MS-DOS looks like. It's a logical construct. It was written to provide a lot of functionality in a small amount of space. Because it's, you might not recall, but back when MS-DOS was out in the early 80s, I think it was 1980, it was released, this first uh, implementation, you have kilobytes of memory, right? Not gigabytes, but kilobytes. And so you didn't have a lot of space in which for your applications to run. So the goal of MS-DOS was to be physically as small as possible because you couldn't afford to have your operating system take up a lot of that space. So MS-DOS is a program that runs, very basic, and it sits as a very thin veneer on top of the device drivers. And the device drivers are pieces of code that interface with the device, almost like the disk controller that we talked about. It was a controller, and it knew on one side how to interact with the hardware for that device, and on the other side presented an API that allowed the operating system, MS-DOS, to set registers in order to elicit certain types of behaviors from these devices. Now, I remember when I was an intern, there were device driver teams, right? It was at Lotus, and it was on the spreadsheet, and you had a team of about 20 or 30 people, and their whole job was to write device drivers that would work with Lotus 123, right? So what Windows did when, consequently, when they came along, what they did is they kind of shifted this burden so that they had a consistent interface for the device manufacturers and a consistent interface for the applications. And so Windows started out as this middleman, if you will, that sat between the devices and the applications. And that made it a much more pleasant, easier experience to write applications. So as an application developer at the time, you didn't have to hire a team of 30 people to keep up to date on all the new devices that came out writing device drivers, right? So that was sort of the early win of Microsoft Windows. And in the beginning, Microsoft Windows didn't run on the native machine. It ran on top of MS-DOS. So you start MS-DOS first, and then start Windows on top of MS-DOS. And you could automate that process with a so-called batch script. Okay. So here we have ROM BIOS devices, right? And that's the basic hardware interface. You have device drivers that talk to that, and then you have a resident system program. Now, one of the big deals, and it might seem like something very mundane by today's standards, one of the big deals that happened with MS-DOS was a command called terminate and stay resident, TSR. And what terminate and stay resident, and I remember that when I was an intern, what it did, it allowed you to exit a program, and then when you exited the program, it didn't kick it out of memory. It allowed it to stay resident in memory, occupying part of memory, so that you could return to it later. It was the beginning of what was called cooperative multitasking. And what cooperative multitasking was, and MS-DOS and the later time could do this, and Windows started out doing that, is that you could run one program and then switch to another program and then switch back to that first program that you were running. And that was made possible by something called TSR command, terminate and stay resident. So it's pretty interesting. So you have this resident system program, you have your DOS commands, and then you also have your application program on top of that. And once the TSR routine came out, it allowed them all to stay in memory, MS-DOS, and that program, so you could switch back, which was pretty cool at the time. All right. So then Unix came. Unix had already been out, but Unix was kind of being developed in among a different community than the MS-DOS folks. And Unix at the time in the earlier days was limited by the hardware functionality. Now they have something called the hardware abstraction layer, or HAL, right? But nonetheless, at the time, Unix was very limited by the underlying hardware you have. And so the Unix OS, one of the big contributions made by Unix was the separation of two main parts, that part that touches the hardware, and that became the kernel, and then the system programs that run on top of that. And so the kernel, more formally in the beginning, was everything that is below the system call interface. So those system calls that allow you to do things like printf and scanf, everything that sits below that interface, i.e. has those implementations, as well as does things like manages the file system, manages your memory, manages the processor, and so forth, that collectively was called the kernel. And so it had, or was responsible for functions like scheduling on the CPU, ushering parts of programs in and out of memory to try to make more efficient use of it, and so forth. All right. Any questions about this? Make sense? Yes? Okay. So this is a traditional Unix. The schematic is a diagram describing the relationship among the parts in a traditional Unix installation. At the bottom, you have the hardware interface, right? That's your hardware abstraction layer. And that includes things like interacting with your terminal, i.e. the keyboard and the mouse and the display. Device controllers for things like peripherals, like your disk drive, network card, and so forth. And memory controllers, things that allow you to access memory devices to get things onto and off of memory. So then the kernel itself includes communication of status between programs through something called signal handling, the I/O system for inputting and outputting terminal drivers, file system, that's swapping. All right, swapping is part of your memory management, and we'll talk about that in detail in the coming weeks. Your control of your disk and your tape for long-term storage, as well as your scheduling and something called page replacement. Pages is the term for the logical construct, which is one of the blocks of your program that you can move onto and off of memory. So we have on top of the kernel that seam between where the kernel meets the applications, you have the system calls. Those are all of those functions that you write in C or access in multiple languages that allow you to make use of all of these services made available by the operating system. And then you also have on top of that things like command line interfaces and shell programs that allow you to run programs that are already pre-written. And then, of course, you have the users that interact with this software. Okay. So this is a so-called layered approach, and a layered approach resembles an operating system kernel. And the reason why they're written or drawn differently is that a kernel can be layered or it can be so-called monolithic kernel, right? A monolithic kernel is just one single body of code, and this code is very tightly integrated with itself. And the reason for that is when you have tight integration, you can have efficiency and speed. Now, early in the, I think, 90s, there was a big argument between a student, Linus Torvalds, who created Linux, and his mentor, Andrew Tannenbaum, who advocated something called the microkernel architecture. And so I'm not going to belabor that, but in a sense, they're both right and they're both wrong, right? The right tool for the right job. Now, monolithic kernels are really important when you have small space or efficiency is what you're after. Microkernel architectures are more flexible, and so if you're constantly adding interfaces, like the ability to do augmented reality, then microkernel, while it can realize a slowdown because you're implementing things as services, you have much more flexibility, right? So it really depends on your application. So in a layered approach, the operating system software is designed into a set of components called layers, and each layer has a certain purpose. As you get to the inner circles in this diagram, you more increasingly get closer to the raw hardware. And so layer 0, sometimes it's called ring 0, is the hardware, and layer 1 would be that code that interfaces directly to the hardware. So on the other or the outer side of each layer, you have a set of APIs that are well-defined interfaces that allow the layer that neighbors it to more easily access certain services. So this third concentric circle right above or outside layer 1 would use the APIs or interfaces made available by layer 1. So now you can imagine in this sort of arrangement for your software, if you change the hardware, so let's say you went from using the Motorola processor to the Intel x86 processor, the only software you have to change is layer 1, and everything else stays the same. So this layering allows you, from a software engineering standpoint, to organize your system so that you have minimal impact every time you want to change something. And likewise, as we go further and further and further out in layering, before we get to the applications layer, which is that outermost layer, layer N, the user interface, you can actually change the way, say, the windowing system works. Maybe you want to change how the buttons behave. You only have to change that layer just on the inside of it, this layer, in order to make that change, and everything else in your system stays the same. So this layering is a software engineering construct, and its purpose with separating the parts of your operating system based on their functionality. And in this particular case, it's based on how close you are in interacting with the hardware. And you only need to change a layer if you want to change the behavior without disturbing the rest of your system. Okay? All right. Any questions about this? So microkernels. Microkernel, in contrast, the idea is to keep the kernel very, very small, hence the name microkernel. And so the kernel in a microkernel architecture only maintains the very basic CPU scheduling and some communication ability, inter-process communication, and that's it. And the idea, from this standpoint, an engineering standpoint, if you make things very, very small, very simple, you can make them very fast. And then everything else in a microkernel architecture, like the file system, the memory management, runtime, and so forth, is implemented as a service. And the idea then is if you want these things to interact, you're going to pass messages between these services. And Mach is a very famous example of a microkernel, and that's the basis of part of Mac OS. So the benefits is that it's easier to extend it. If you want to change the memory management policy or the way the file system works, you can do that very easily in a microkernel architecture. You just change the file system service or change the memory management service, and the rest just continues to work, right? So here's an example of microkernel architecture, or at least a schematic. You have the basic hardware down below. Then you have the microkernel, and that has, in this case, CPU scheduling, memory management, and inter-process communication. So things like the file system, things like the device drivers, that's all implemented as a service. And whenever you want to make use of the file system or device drivers, you pass a message. And so by keeping as few parts as possible in the microkernel, you can make it very, very fast, very high performance, finely tuned. But the consequence of making things like a file system type of service is that it's much slower to trap between kernel mode and user mode, passing these messages in order to make use of a file system. The good news is that the benefit is that you have much more flexibility. You can change this file system without having to recompile the entire operating system, which is not the case in a layered approach or the monolithic approach. Okay. Any questions about this? Make sense? Okay. So modules is another method for structuring some of the behaviors for an operating system. And a module takes a kind of object-oriented approach, and you have parts of your operating system, let's say the networking or communication APIs, they're collected together as a shared object or library, and you can load these things dynamically in order to change basic behavior of the operating system. So you want to change the way that communication is implemented. Maybe you want to change your TCP stack to have different behaviors. Well, in something like Linux, which is monolithic, you'd go into the source code, you'd make those changes, you'd recompile it, and then you have to reinstall the bootloader and the operating system. Okay. In something like a system that uses so-called kernel loadable modules, you just compile that module and then you just update that module on your operating system. And the interesting part about modules is that you don't have to stop or reboot your machine, right? You just load the new module and you're up and going with the new features. Okay, so they use object-oriented approach. Each core component is separate. So you might have a different module for your networking system, for your user interface components and stuff like that. And each is loadable as needed within the kernel. So if you ever tinker around with the internals of Mac OS and you see a message about something called a kernel extension on Mac OS is nothing more than a kernel loadable module, right? Things like Carbonite use kernel loadable modules or kernel extensions as they're called on Mac OS. And so they're kind of like layers, but these layers, if you will, are collected together as shared objects, and you can load them dynamically and unload them without having to recompile, reboot, or reinstall the operating system. Okay. So Solaris, which was the variant of Unix that was offered by Sun Microsystems, is a famous example of using kernel loadable modules. You have the core kernel, so that did things like memory management, CPU scheduling, and you had all these modules here, these blue circles, for things like system calls. You could load and unload new implementations, file system, all sorts of stuff, streams, the interpretation of executable binary formats. It was amazing, bless you, what you could change without having to stop the operating system. And that was made possible by these kernel loadable modules, or as macOS calls them, kernel extensions. Okay. So you also have hybrids, and you can mix and match these things that I talked about before. You can combine lots of different approaches to get all sorts of things. Everything that I've talked about isn't an all or nothing deal. You can certainly mix and match modules with microkernel and all sorts of stuff like that. Linux and Solaris in the kernel are in the address space. They're monolithic, but they also use dynamic loading of kernel modules. So they're monolithic operating systems with kernel modules. Windows is mostly monolithic, but you have microkernel-like personalities, as they call it, services for different subsystems. Mac OS is also hybrid. It's layered, but you also have microkernel-like features for Mac OS. Okay. So this is the macOS structure. You have parts of Mach, which is microkernel, BSD, which is monolithic. You have hardware abstractions at the bottom, the I/O kit, and kernel extensions, which are your kernel loadable modules that I just alluded to. Now, on top of your basic kernel, you have application environments. So you have things like QuickTime, which is their multimedia format, but there are also services associated with that. You have Cocoa, which is their interface technology. No, you have their, I forgot what Cocoa is. I can't remember. Cocoa is their, I think it's their systems call interface. And then Java, of course, is there, the programming environment. You also have Objective-C. I can't leave out Objective-C. And then on top of that, you have Aqua, their basic graphical user interface technology. Okay, so iOS is their mobile device, Apple's mobile device operating system. You have the core operating system. You have services for the operating system, so things like file system, memory management, stuff like that. You have your media services because there are a lot of media devices associated with your device, with your iOS devices. And then you have Cocoa Touch, which is the inputting of gestures for your touch screen and the tracking of, of interactions with that I/O device. And so iOS started based on macOS, but it added functionality specific to your mobile device, and a lot of it has to do with I/O as it pertains to the touchscreen. It doesn't run OS X applications. It uses a different CPU. It uses the ARM CPU, Advanced RISC machines, instead of the Intel architecture, which is what the desktop and laptop are running for now. Right? That might change in the future. We also have okay, Cocoa Touch is the Objective-C API for developing your app. So it's your application programming interface, all of your system calls. It has stuff like media and core services for things like storage and cloud. Android. Android was developed by a consortium, and that consortium, the biggest contributor was Google. It's open source, so you could take the Android source code base, take a piece of hardware, customize it to suit, and start selling it if you wanted to. It has a similar stack to iOS, but they call them different names. It's based on Linux, but it's been modified to provide things like memory management, device driver management specific to those mobile devices. Because when you're mobile, you're concerned about things like power, so you can't do things the same way. So they took this plain vanilla Linux, which is intended for desktops, and customized it in order to run on mobile devices. Okay, so what's the time here? Okay, we have 20 minutes. So Android includes a runtime environment, right? The ability to execute applications. It also has a virtual machine that allows you to interpret the binaries in order to run them. And it also has Java support. And so it has the Java class files and runtime and a virtual machine, the Dalvik VM, in order to execute your Java bytecode. So it has libraries and frameworks for doing all sorts of things like SQL, multimedia, and so forth. It has libc, the C runtime library, and that libc is what you're using when you do things like printf and scanf. It's a standard programmatic interface for system calls on Unix type systems. This is the Android architecture. So you have your libraries here. So SQL, OpenGL for doing rendering of graphics. You have WebKit, and then you have the runtime. your core libraries, and the virtual machine. On top of all of that, you have your application framework. Okay. So let's take a look lastly at booting, debugging, and system tuning. When you're debugging an operating system, it is a very complex journey, but it's very, very doable. And so there are many facilities in an operating system for you to figure out when things are going right and when things are going wrong. And so when you're trying to find and fix errors, one of the facilities in your operating system is so-called log files. And these log files are text files that are written out to special parts of your file system. And these text files are written out regularly by programs and by your operating system, and it reports on the status of various operations. And so one of the tools that you have to figure out what's going on, especially for things like file system and communication system, is your logging subsystem. Now, logging, some logs are turned on when you boot your operating system. Some logs you actually have to turn on by altering your kernel to turn on system logging, because when you have full system logging turned on, it's a lot slower. Your operating system run is slower because you're taking time, pausing for I/O to write these entries to disk, which incurs a slowdown. And so when an application fails, one of the things that happens is a so-called core dump. And core is a historical name for memory. And a core dump consists of a status of your CPU and memory and a little bit about your file system that's written out to disk if an application crashes. Now, if you've ever run, say, Mac OS and you get this crash report, right? A window pops up and says, your system crashed. Would you like to send it to the vendor, right? And you could say yes or no. Well, if you look inside the text of that crash report, that's exactly a core dump, right? It'll show you the status of the registers on the CPU. It'll show you status about the stack. It'll show you a little bit about what happens with RAM and so forth. And so a core dump is essentially a snapshot of all of the resources the offending CPU was using or had associated with it when it crashed. Okay, and so when an operating system fails, it can generate something called a crash dump file. And that crash dump file is nothing more than a core dump for the OS kernel, right? And they call it different things to distinguish between whether or not it's for an application or the kernel itself, since the kernel is very special and very different from a typical application. So beyond crashes, you can also compute what's called a trace. And you can literally list all the activities or function calls that a program or the kernel takes in order to analyze what's going on. Now, as you can imagine, when you have tracing turned on, your system is a lot slower, but you can at least debug what's going on it. Profiling is the collection of statistics about function calls. And what you're after with profiling is to know what functions are your so-called hotspots, which ones are being called the most. When you want to tune the performance of your system or make it run faster, well, where do you make those optimizations? You make it in those places that are used more frequently. And so the first thing you would do, in fact, on NetBeans, there's a profiler. MATLAB has something that looks like a profiler. So if you have a large program and it's not running fast enough for you, you would run your profiler and use that to execute your program. It samples the function call execution, writes down statistics for that, and then you look for those functions that are called most frequently, and then you start those in those places with your optimizations. Okay? All right. Any questions about this? No. So one of the things you also have available to you are these system reports. And this is the Windows Task Manager, but there's a similar interface in Mac OS. We can look at the resource consumption associated with your applications. So for example, when I render the videos that I post on the channel for this class and the other class that I'm teaching, undergrad classes, I like to look at this the performance of iMovie, which is what I use to edit and render the video, because I want to know how much memory it's using, how many resources, how much processor it's using. So you can actually get live statistics with performance meters like this, whether Windows or Mac OS. So for example, you're on your machine's really sluggish, you don't know why, so you bring up the performance meter and you look at which processes are taking the most CPU, how active your disk drive is, how active your network card is, and so forth. right? So this tool allows you to take an active snapshot, if you will, of all of the resources being used on your machine and which processes are using these. Okay. Another one is on Solaris. It's called dtrace, and dtrace allows you, called debugging trace, allows you to literally see the function calls that are happening in your system. Again, this is a very expensive tool to use, but if you want to see what's happening in terms of your performance and the behavior, the system call, the function call behavior of your programs, it's worthwhile to use something like dtrace. It uses a lot of disk space. So of course, if you're going to turn on something like dtrace, you want to make sure that you have ample storage available, but it's immensely useful. And so dtrace works with a series of probes, and a probe is nothing more than a snapshot when a certain event occurs, and that snapshot corresponds to the function calls that are being made. And so it also, when it fires, this example here on the screen on the right-hand side in Courier font is an example of a dtrace output. Okay. Now, if you know all the functions, and this is for X11, which is a windowing system on Unixes, it's not important what it is, but just to show you a very, very small snippet of what a dtrace output would be. And so here you have X events queued. The next thing it calls is underscore X events queued, X11 transfer bytes, readable bytes, and so forth. So it shows you the call stack, and it shows you the returns from those calls, and it shows you the system calls, I/O control, and so forth. Okay. It looks like there's a lot going on there because there is, but if you're debugging low-level systems, tools like dtrace alongside with logging and the performance meter are immensely useful to get a true picture of what's happening on your system. Okay. Any questions about this? So that's a little bit more in dtrace. I won't belabor that since that's not a big focus of this class. I recommend if you're interested in stuff like dtrace for doing kernel debugging, I would recommend you Google search. There's lots and lots of tutorial information out there. So operating system generation. How do you compile, how do you create an operating system? Operating system typically have, fairly large, the kernel's not too big, but if you take all the other system libraries together, it's a lot of code. And so typically, you don't just compile everything that you have available in your source code. You make these choices based on what's important to you. And that process of making choices based on what is important to you is called system generation. So you generate your operating system based on what you want. And so they're designed, operating systems are, they're designed to run on a lot of different types of hardware and a lot of different types of machines. And so it's not very wise to pull in all that code and compile it together. You only want to pull in subsets of that code that are useful for your particular machine and target platform. And so what the sysgen does is it gathers information about the platform. What type of processor do you have? What type of hardware do you have? And it then selects out pieces of your code base necessary to engage with that. So the sysgen builds system-specific compiled kernels, and it also can generate much more efficient code because you don't want to install a block device if you don't have a block device. If you have a character device, you want to install the code for a character device and use that to build your operating system. Now, this is very related to something like autoconf and configure. And when you download Linux kernels, maybe if time permits, we'll go through an exercise of actually compiling a Linux kernel. We'll see how the balance of the semester goes. Okay, so the system generation allows you to subselect parts of source code and only compile those parts of the source code together to build your kernel for hardware that you actually have on the platform in particular. System boot. So what happens when you turn on the machine? You turn on the machine, and the first thing that happens is a lot of system integrity checks occur, and that's driven by the bit input output system, which is part of your firmware, right? That's something in hardware. And there's a small piece of code called a bootstrap loader, and that's stored in read-only memory or electrically erasable read-only memory, or programmable read-only memory, or EEPROM. And what this bootstrap loader does is it locates your kernel. Now, it can either locate your kernel directly and load that, and your operating system has control of the machine, or it can locate your kernel indirectly through something called a bootloader. And so when you start a Linux distribution, you're starting the bootloader called grub, right? And that gives you a menu, and you can scroll through that menu and select one of a different number of versions of Linux or different operating systems. And this bootloader is loaded by the bootstrap loader, this grub, and grub takes control of the machine and allows you to select an operating system to boot from a menu, right? So it involves some user input. Now, typically when you use grub, there's a so-called default choice. It's that one that has a little asterisk next to it. So next time you load Ubuntu, look at what happens when you first boot the virtual machine from a powered off state, and you'll actually see the grub bootloader present you with a menu, and then it loads Ubuntu. But you could certainly install more than one operating system, and that bootloader will present you a choice of each of those operating systems you've loaded, and it's up to you to choose one. If you don't, it'll select the default. So this is grub, and this is involved in the system boot process. So with that, we have finished. If any questions, final questions? We finished the introductory material for Chapter 1 and Chapter 2. And on Thursday, we'll start with more of the internals, and we'll change our focus to processes.